Hello, Algebra 2 students. This is Miss Prater, and this is a recording of the lesson 801 through 803. I'll be out of the office Monday, April what would that be? The 14th. I'll be out of the office, and this would have been the lesson that I would have taught in our live class connect. So the first thing I do want you to think about is, what do the words row and column mean? Because I think it's really important as we start our new unit on matrices, which is in Unit 8, we really need to know what a row and what a column is. So on my next slide, I made a visual of some things that I think of or come to my mind when I think about the word rows. So usually I think about a movie theater. The seats are in rows. This doesn't look like a movie theater. This kind of looks like just chairs in a large room, but chairs could be in rows if you're thinking about those rows being left to right. Definitely in a movie theater, the seats are attached. Most likely, the seats are attached in a movie theater, and the seats go in rows like this. I also think about the eye chart. I've had glasses since I was 8 years old, and sometimes I wear glasses, sometimes I wear contacts. But when you go to the eye doctor, if you've ever been to the eye doctor, which I would think most of you probably have, or you have had a screening at your school when you were younger, you call those letters out in rows, going from left to right. And when I think about columns, the first thing I think about are the columns that are in front of a building or maybe a house. And then I don't know why I decided to put the Connect 4 game, because the Connect 4 game, we could win the game by having the same colored, I would call those checkers. I know this is not a checker game, but those little plastic pieces that are circles. If you went from left to right, those would be columns, and if you go up and down, those would be rows. So big picture here is a column is going to go left to right always, and a row is going to go up and down always. So when we talk about matrices, one of the first things that we talk about rows and columns, and we'll get to that in just a second. This is April 14th, 15th, 16th, 17th, and 18th. And we start a new unit this week covering matrices. 801 is Introduction to Matrices. 802 is Multiplying a Matrix by a Scalar. And 803 is Adding and Subtracting Matrices. This is a built-in unit. Not all Algebra 2 classes in the United States include matrices. So because we live in Alabama, we had to add in our own videos for Unit 8, so that's why it's going to look a little bit different, is we had to build that in. So my lesson today is going to cover Monday, Tuesday, and Wednesday. Wednesday's lesson this week, there's not a whole lot to do in 801, or really a whole lot to do in 802, so that's kind of why I decided I would just push all those together. And then Wednesday's lesson will be on multiplying matrices, which is probably one of the most difficult things we'll do in this unit. Not that it's like the worst thing in the whole world. And then Friday is a staff work day, and there will be no students or no classes taught on Friday. So all your classes should be canceled on Friday. A matrix by definition, so let's take a minute and talk about our vocabulary. We know vocabulary is very important. If we don't know what the word means and they're asking us to find a word, that's going to make it pretty hard for us to be able to answer the question. But a matrix is a rectangular table of numbers arranged in rows and columns. So most of the time a matrix is going to have brackets on the left and brackets on the right, and they're going to have rows and columns. So sometimes you just have, like one row. A matrix could look like that. It could have one column. It could have 3 rows and 3 columns. It could be like this. This would be 3 rows and 3 columns. It just has to be in the shape of a rectangle. Remember, a rectangle could have the same number of rows as it does columns, or it could have, in this case, this matrix has 2 rows and 3 columns, but it just has to be in the shape of a rectangle. One of the first things they want you to know is they want you to know what the dimensions of a matrix is. And we always do rows by columns. So first of all, you're going to have to know that the R comes before the C. And so some of the things that my students have talked about in the past that help them remember, it's rows first and then columns, is RC Cola, which is a cheap, old-fashioned Pepsi or a Coke, usually in a blue can. What else have they used? Remote control. And sometimes they use some type of candy, RC, Reese's maybe, like a candy bar. I guess it's spelled like this. But anyway, you need to remember that rows do come before columns. So when I do the dimensions here, I count the number of rows. So that's 1 row, 2 rows, by the number of columns, 1, 2, 3. So I'm going to change my colors and just kind of show you this. So my rows I'll do in pink. There are 2 rows. Rows always go left to right. And then I'll do my columns in blue. My columns always go up and down. So that's 1 column, 2 columns, and 3 columns. So sometimes the problem will just ask you what are the dimensions of your matrix. And they want to know the number of rows by the number of columns. And this X does not mean multiply. It means the word by. So dimensions. Here are just some examples of where they're asking us to find dimensions. I'm going to make my pen a little bit darker. So find the dimensions. So remember, we're doing rows by columns. So this problem has 1 row, 2 rows, 3 rows. So my first number is 3. And it has 1 column. So the dimensions would be 3 by 1. This matrix has 1 row. So it's going to be 1 by, and it has 1 column, 2 columns, and 3 columns. So the dimensions would be 1 by 3. This matrix has 1, 2, 3 rows, and 1, 2, 3 columns. So it would be a 3 by 3. Rows by columns are RC Cola, remote control, Reese cup, however you want to remember that. Rows by columns. Rows always go left to right. Columns always go up and down. In my second example, we're going to do something called scalar multiplication. And what's going to happen is you're going to have a matrix that's going to have rows and columns in it, and then you're going to have a number out in front. This is 3 different examples. You've got a matrix which has rows and columns, and then you've got a number out in front. Well, that number, it doesn't say 6 plus, 6 minus. It's just pushed right up next to the left bracket. That means understood multiplication. So you're just going to multiply everything in your matrix by 6. So 6 times 5 is 30. 6 times 7 is 42. 6 times negative 3 is negative 18. And then you would put the bracket back on your answer. So that would be your answer. In the second example, everything in our matrix gets multiplied by the scalar negative 3. This outside number is called a scalar. That's why it's called scalar multiplication. So negative 3 times 6 is negative 18. Negative 3 times negative 2 is positive 6. Negative 3 times negative 5 is positive 15. And then we put the brackets back around. In the last example, the scalar is 5, and we've got to multiply everything by 5. So it's pretty well self-explanatory. You just need to make sure you don't make any careless mistakes. So I usually probably multiply pretty quickly, and then I'll go back and check for any careless mistakes that I may have made, because I am a human being and I make mistakes all the time. So I'm just going to double check, multiplying everything by 5. I think I'm good there. All right, scalar multiplication, not too bad. Much easier than multiplying a matrix times another matrix. So when adding, let's take a look at what's in this yellow box. When adding and subtracting, your matrices do have to have the same dimensions for you to be able to add, and it'll have to be the same. Somehow that did not get in my yellow box. Just a reminder in the aqua box that dimensions are always written as rows by columns. So let's take matrix A. Okay, we could add matrix A with matrix B because matrix A has 2 rows and 2 columns. Matrix B also has 2 rows and 2 columns. So we're only going to be able to add or subtract if our matrices have the same dimensions. So let's move on to matrix C. And we would be able to, let's go back and put add or subtract. Just kind of talking about what's possible. So matrix C is 2 rows and 3 columns. And I would be able to add or subtract that with matrix D because D also has 2 rows and 3 columns. Same thing with E and F. E and F have the same dimensions, so we would be able to add or subtract E and F. And G and H have the same dimensions, so we could add and subtract G and F. We're not going to actually do that. G and H, excuse me. G and H both have 3 rows and 3 columns. And then U and V, little u and little v matrix could be added or subtracted because they both have 2 rows and 1 column. 2 rows and 1 column. And W actually, it has 3 rows and 1 column, and it could not be added or subtracted to anything on there. So key here is you have to have the same dimensions to add or subtract. In the next couple slides, we'll actually practice adding and subtracting. And it's not too bad. So in problem number 3, we have this matrix, and they're asking you to add it to this matrix. Sometimes it's possible if the dimensions are the same. Both of these are 3 rows, excuse me, and 2 columns, 3 rows and 2 columns, so it is possible. So when you add the numbers that are in the same spot. So you're going to add the -6 with the -4. The -3 will be added to the -2. The -6 will be added to the -1. The 4 will be added with a 4. The -6 will be added with a +5. And the 5 will be added with the 3. So you're just adding the terms that are in the same location. So I'm going to double check. -10, -5, -3 plus -1 is -7, 4 plus 4 is 8, -6 plus 5 is -1, 5 plus 3 is 8. And I was just trying to highlight the numbers that were in the same location. So top left with top left. Top left is added to top left. Top right is added to top right. Middle left is added with middle left. Middle right is added with middle right, and so on. In number 4, we can subtract these because I have 1 row and 4 columns in the first matrix, 1 row and 4 columns in the second matrix. So we will be able to add these. The -3, we will be able to subtract these. -3 minus 3 is -6. 1 minus -1 is really 1 plus 1, which is 2. 4 minus -2 is really 4 plus 2, which is 6. And 3 minus -3 is really 3 plus 3, which is 6. Just be careful when we subtract. I always like to say subtraction is the devil and it will cause you to make mistakes. So just be careful when you're subtracting. And then you just subtract, as long as your matrices have the same dimensions, you subtract the terms that are in the same location. So not too bad. All right, we've got 3 more slides. You can get a little bit more difficult. Number 6, when I looked at number 6, I thought that's a little bit more difficult. But Number 5 is not possible, and sometimes they'll throw one of these in. Sometimes instead of it saying not possible, it might say not defined, which just means you can't do it. But this first matrix has 2 rows and 3 columns. And the second matrix has 4 rows and 1 column. So remember, you can't add or subtract matrices by definition unless they have the same dimensions. So sometimes they might trick you and ask you to add or subtract, but as long as the dimensions are different, that means it's not possible. In number 6, it is going to be possible to add and subtract these 3 matrices, but I would just suggest that you take this problem slow and you don't look at all 3. So just think about, if you had the number 10 plus 2 minus 7. You would start from left to right because that's your order of operations. If you have addition and subtraction, you would add the 10 and the 2 first. That would give you 12, and then you would subtract 7 and you would get 5. So we're going to practice that same thought. If we're adding and subtracting, we're going to start on the left with 2 matrices at a time, and we'll go from left to right. So we'll start with the first 2 matrices because they come first from left to right, and the problem is asking us to add. So we'll do 5 plus 3 is 8, 3 plus 5 is 8, negative 6 plus 6 is 0, negative 1 plus 0 is negative 1, negative 3 plus 2 is negative 1, 4 plus negative 2 is 2. So that's what I get when I add the 2 first matrices. I'm going to double check because these are so easy to make a careless mistake in. And then we're subtracting right here this last matrix. 1, 2, 4, 5, 3, negative 2. So then we'll do these 2 matrices. Just do 2 at a time. So 8 minus 1 is 7. Let's see if I can squeeze this in. 8 minus 2 is 6. 0 minus 4 is negative 4. Negative 1 minus 5 is negative 6. Negative 1 minus 3 is negative 4. And negative 1 minus negative 2 is really negative 1 plus 2, which would be a positive 1. And then you put your brackets around your final answer. So just kind of take your time if you have more than 2 matrices to add or subtract. Same thing in this problem. We do have something in parentheses here, so we'll follow our operations and we'll actually multiply this scalar of positive 3 first. So we'll bring down the negative 3. We'll multiply this scalar, since it's inside our parentheses, times everything that's in our matrix. That's going to give us negative 6, 0, 12, and negative 9. And then we'll take this outer scalar and we'll multiply it times everything on the inside. So that'll give me 18, 0, negative 36, and 27. Sometimes they ask us to add things that aren't like terms, and so I thought this was an example of something that maybe you think that you couldn't do or it wasn't possible. But z plus 2, even though I don't know what z is, that's one value. Okay, z plus 2 is one value. Even though it's 2 terms, those 2 terms are separated by a plus, so that represents one value, and y plus y squared is one value. So I have one value here, one value here, so that means I have 2 rows, and then I have 1 column. Same thing here, 2 rows, 1 column. So I would add this quantity, even though it's got 2 terms, it's separated by a plus, so that's one quantity plus this quantity. That's going to be z plus 2 plus 6y. None of those are like terms, so I cannot actually add them. And then I'll add this quantity with this quantity, and that's going to give me y plus y squared minus 5x squared. And then we just have to leave it like that. So this looks kind of weird. I thought this was a good example for us to talk about. So z plus 2 plus 6y. If I knew what z and y were, that would give me one number. And same thing down here. If I knew where y and x were and I could plug those in, that would give me one number. So that's why it's 1, 2, 2 rows, 1 column. And there that would be as far as you could go, just because you have, unlike terms here. That's a 2, not a z. All right, I think I have one more slide. This one again is just more than one thing to do. We start with parentheses. We would subtract these two matrices, so we would take the 3, which is called the scalar, and we would bring it down, and we would get x squared minus 4y. I'm going to put this in parentheses because I think it might kind of help you see. So that's one term, and then 4 minus 1, which is 3, and then negative 5y minus, this is going to be negative 5y minus y minus x. And then negative 3x minus negative 3x, which is really going to be negative 3x plus 3x, and those will cancel and give you 0. And then 6y minus x, and then negative 4 minus 5. Before I multiply my scalar of 3, I am going to simplify because I do see I have some like terms here. So I'm going to end up with x squared minus 4y. That'll be like one term. Then we got 3. Negative 5y minus y is going to give me negative 6y minus x. Still got the 0. And then 6y minus x. Don't have any like terms there. And then negative 9. And then the last thing I'll do is I'll multiply everything in this whole entire matrix by 3. So I'm going to go up here so I have a little bit more room. That's going to give me 3 times x squared is 3x squared. 3 times negative 4y is negative 12y. 3 times negative 6 is negative 12y. 3 times negative x is negative 3x. 3 times 6y is 18y. 3 times negative x is negative 3x. If you want to put these in parentheses, you can.